Okay, let's do a slightly different example of a game where one player has two strategies. So here we have the row player has two strategies and the column player has three strategies. And let's see, is there any strategy here that is dominating? I don't think there is. You can check and see. Right. So let's assume that the row player has a mixed strategy, P1, P2, and then the column player has a payoff for each different column that he can choose. If the column player chooses the first column, well, then his payoff is 3 with probability 1 minus P2 and 0 with probability P2. So that's 3 times 1 minus P2 plus 0 times P2, and you get 3 minus 3 P2. If the column player chooses column 2, he gets 1 with probability P1 and 1 with probability P2, and that works out to 1. And if the column player chooses column 3, he gets 0 with probability P1, 3 with probability P2, you get 3 P2 here. Alright, so we've got this. And we can graph these three graphs, y as a function of P2, and you get a graph like this. Right? Now just like before, these three lines, 1, 2, 3, represent the column player's payoff depending on which column he chooses. Right? So for instance, if the row player chooses down here like 1/6, he chooses P2 equals 1/6, the column player is going to choose column 3 because column 3 minimizes the row player's payoff. Now an interesting thing here is that if the row player plays anything between 1/3 and 2/3, if the row player chooses P2 anything between 1/3 and 2/3, then the column player is going to choose column 2 and his payoff is going to be 1. Right? Now remember, the row player wants to maximize the payoff, knowing that the column player is going to try to minimize. Okay? So the column player, whatever P2 the row player chooses, the column player is going to choose the constraint, choose the row that puts him on this solid black line. So as long as the row player chooses P2 between 1/3 and 2/3, he's always going to get the same payoff. So in fact, there's not just one optimal strategy. He could choose P2 equals 1/3, he could choose P2 equals 1/2, he could choose P2 equals 2/3, and no matter what he chooses, the expected payoff is going to be the same because the column player is going to choose column 2. That's his option. Right. So here we have the endpoints of the flat area are a 1/3, 2/3, and 2/3, 1/3. I'm sorry. This is P2 equals 1/3. So this would correspond to 2/3, 1/3, and this corresponds to P2 equals 2/3. So P1 equals 1/3. So these 2 points here correspond to these 2 points here, and these both represent strategies. And any strategy in the middle, which is what we would call a convex combination, is a mixture of these two, where the sum of the coefficients is 1. So no matter what A is, as long as A is between 0 and 1, this is going to be an optimal strategy. Okay. And as I said, the column player is going to choose the second column, and the value is going to be 1. That's the payoff, what the payoff is going to be. Right. So what this says is that if you have two optimal strategies, then you can kind of mix those two optimal strategies and get another optimal strategy. So any so-called convex mixture of optimal strategies is also an optimal strategy. Okay, and that's what the picture up there shows. Okay. All right, now so far we've looked at cases where the row player has two strategies, column player has more. Now we're going to look at the column player having two strategies, row player have more. Now really this is just the very same thing, only the roles of maximum and minimum have been reversed. All right, we assume the column player has a mixed strategy, Q1, Q2, and then we evaluate the options for the row player. If the row player chooses row 1, his payoff is 6Q1 plus minus 1Q2, and that works out to this value, 6 minus 7Q2. If the row player chooses row 2, 0Q1 plus 4Q2 gives you 4Q2. The row player chooses row 3, 4Q1 plus 3Q2. Remember, Q1 is 1 minus Q2. You end up with 4 minus Q2. You plot all of these. And remember now, these represent the choices of the row player. The row player is always going to choose his maximum payoff. So for instance, down here when Q2 is small, maybe Q2 equals 0.1, then the row player is going to choose row 1 because that's going to give him his biggest payoff. In between here, he's going to choose row 3. Here, he's going to choose row 2. Now, where's the minimum payoff that the column player can get if the row player plays along this solid black line? Remember, the column player wants to minimize. So if the row player goes here, if the column player goes here, then he's going to minimize the payoff for the row player when the row player plays his best strategy. Right? So it's basically just the flip side of the previous case. This is you can say this is the minimax. This 4/5 represents the the probability Q2, which is the probability of choosing the second column for the column player. So that gives me my optimal strategy for the column player. Now what about the row player? Well, in this case, for the row player, only row 2 and row 3 figure in the mix. Row 1 doesn't figure in the mix. So we really have 2 rows and 2 columns. We have a 2x2 game that we can solve by the previous formulas and get the row player's strategy as well. Okay. Now, of course, the row player has 3 possible rows, but as we said, the row 1 doesn't figure in this minimum point. So row 1 gives me a 0, and I get 1/5, 2/5 for row 2, row 3. Okay. Now, this method really is only good for games where you have 2 non-dominated strategies because it's hard to graph in higher dimensions. All right, now one more thing from this section. We're going to use this theorem in the next section. And what this theorem basically says is, if I add the same number to every entry in the payoff matrix, then the best strategy is the same. And that's really quite clear from this picture, because if you add the same number to every payoff, it just shifts the entire graph up. The minimum point is the same. The mixture of optimum strategies is the same. It's just the payoff has changed. The value of the game has changed. If I change every entry in the payoff matrix by k, then the value is going to change also by k. But the optimal strategy does not change. And the important thing about this is that in the next section we'll find out that we need a game in which all of the values in the payoff matrix are positive. So that's easy to do. Just add a big enough k, and that will make the entire payoff matrix positive. Right? So that's good for this video.